Po-Chuan Yang, who is a general manager at heterojunction business unit of Ryzen Energy, one of the early adopters of the technology. So he's going to talk on progress of heterojunction technology and key milestones at Ryzen. Po-Chuan, the floor is yours.
Hello, can you see it? Can you hear me?
Yeah.
Okay. Okay, so hello everyone. Thanks TaiyangNews to give me this opportunity to talk here. I'm Po-Chuan Yang from Ryzen Energy. So today I want to share heterojunction status in Ryzen. So this is my agenda today. At the beginning, I will explain why Ryzen choose heterojunction as our new platform for next generation cell technology, and we think heterojunction era is coming. Then introducing our Hyper-ion heterojunction product from cell module to system level, and update our capacity planning for Hyper-ion this year and the next year. As you can see, solar is becoming mainstream energy in the world. That is because we are keep decreasing levelized cost of energy and the carbon footprint during cell and module production. Key factors to decrease carbon footprint are like low temperature process and the thin wafer thickness, less cell process steps, and also some module materials. So, and for lower levelized cost of energy, we need to consider higher front side and the rear side cell efficiency, and also stable temperature coefficient and better power output during low light condition. So we can easily find that heterojunction is the only technology to fulfill these targets at the same time. So that is why we are thinking about heterojunction is the future technology, and we are focused on this technology right now. So according to CPIS prediction, PERC P-type cell will stop expansion and phase out very quickly, and some PERC capacity will upgrade to TOPCon technology. Some new players will go for TOPCon or heterojunction directly. So finally, in 2030, we target N-type cell will dominate over half market, and like BC type cell is monofacial, and will focus on only like rooftop market. Will with roughly 5% market share in the end. So I think a lot of people are talking about TOPCon and the heterojunction efficiency status in real production. So here I would like to share some data in Ryzen, because actually we have 3 teams to do PERC cell, TOPCon cell, and heterojunction cell development. So we can compare these 3 kinds of technology at the same time. That means we can use the same wafer size and the same module type and compare apple to apple. So in this case, we can find that TOPCon module is higher than PERC module, roughly 15 to 20%, 20 watt, and the heterojunction is higher than TOPCon, roughly 20 to 30 watt. So considering the bifaciality, we can also find that TOPCon is roughly 80 plus minus 5%, and the heterojunction is 85% plus minus 5%. So and the last one is the temperature coefficient. Heterojunction has the lowest temperature coefficient, so it can has better power output in the real status. So Ryzen got the highest 25.5% cell efficiency with 120 micrometer wafer and double side microcrystal silicon double layer in 2021 Q4. And this wafer thickness is low wafer thickness, which means roughly only 100 micrometer wafer after texturing process. So here I would like to talking about heterojunction milestone. We started heterojunction activity from 3 years ago and built 100 megawatt pilot line at the same time. We offer Seeger heterojunction module with M2 wafer from 2020 and is the shipment #1 in China during 2020 and 2021, these 2 years. Last year, Ryzen heterojunction team broke the module world record from 3 times. And finally, we achieved 23.65 module efficiency. On December last year, at the beginning of this year, we upgraded the pilot line to G12 half wafer and increased capacity to 500 megawatt. And we launched the Hyper-ion product, which is using G12 half wafer and using 24 busbar technology. We also got the world's first TUV certification of G12 heterojunction high efficiency thin wafer module on August this year, and start to ship our Hyper-ion module to our customer right now. The most important thing is we are building the first 5 gigawatt heterojunction cell and the 5 gigawatt heterojunction module factory right now, and the target to produce first cell at Q1 next year. And the second half next year, we plan to build another 10 gigawatt cell and 10 gigawatt module. Totally, we will achieve 15 gigawatt capacity at the end of next year. This is our heterojunction product planning. We will roll out a 700 watt product at the beginning. This is focused on utility scale. And the other 3 types of commercial and industrial rooftop and residential rooftop application will be coming soon. So basically, there are 6 features for our Hyper-ion heterojunction product. The first one is G12 half wafer with 120 micrometer wafer thickness. And the second one is 24 busbar. This is our patent module technology, which is invented to adapt for heterojunction ultra thin cell. And actually, this 24 busbar means 24 busbar on module level, but actually in cell level, this is 0 busbar cell design. So that means we can save a lot of metallization cost in busbar area. And the third one is we are using the low silver content path to save the metallization cost. In this case, we can achieve very low cost metallization level and achieve roughly 10 milligram per watt pure silver content. Number 4 is we are using steel frame. There are 2 advantages. First one is carbon footprint is lower than aluminum frame, and the overall stiffness of aluminum frame can meet the demand, but the local stiffness is weaker. So we think steel frame is very good product to integrate with our heterojunction cell. And number 5, sorry, higher energy yield coming from heterojunctions, lower temperature coefficient and higher bifaciality. And the last one is low degradation from our double glass module design, and there is no LID and the PID issue. So here I would like to talking about thin wafer production status. Actually, we started from 150 micrometer wafer. After that, we decreased 10 micrometer and it takes several weeks to solve the issue during production, not only cell, but also module production, and then decreasing to 130, and it takes roughly longer than one, we are doing from 150 to 140. Then 120 takes half a year. So right now we have clear path to 80 micrometer wafer thickness, and has confident we can do mass production in the near future. So here, talking about 24 busbar design, like I mentioned, actually in cell level, this is 0 busbar design, but since we are a module maker and we just provide the module to our customer, so we will not focus on how many busbar we are using on cell level. But finally, this is 24 busbar design in module level. So if we have more busbar, that means conduction distance will be shorter, and reducing the current density and also power loss, and increasing the cell tolerance to microcracks and the finger breakage. And the most important thing is busbar and the finger contact points increase 2 times. That means the module reliability will be better compared to 12 busbar design. And talking about microcrystallized silicon doping layer, it can improve ISC and the fill factor. For ISC, it is because that microcrystal silicon layer light absorption coefficient is much lower compared to amorphous silicon layer. And also we will introduce some like oxygen or carbon to increase the band gap between the in the microcrystal silicon layer. Therefore, the short wavelength response is better. And for fill factor, that is because the microcrystal silicon has better conductivity. Therefore, it will decrease the serial resistance in the cell, and in the end, we got a higher fill factor compared to using amorphous silicon layer. For metallization process, there are 2 shortcomings for our design right now. The first one is we are using low temperature past or copper past, and the conductivity is bad, and the finger width is wider compared to high temperature silver past. Therefore, we are looking for better metallization method to overcome this problem. For example, copper plating is one of the candidates to solve this problem. With good pattern mask, it can achieve 18.1 micrometer finger width very easily. In this case, we can have higher ISC and also got very good fill factor because that is pure copper line compared to the low temperature silver past. And another kind of candidate to improve the metallization is the laser pattern transfer printing. We will, because we fill the groove with past first, then using laser to transfer the past on the cell. In this case, we can achieve very good aspect ratio, and there is no damage on cell level since it is non-contact printing method. So here I would like to explain why Hyper-ion product result in super low carbon footprint, which is 400 value. The first one is only 4 cell process steps, temperature in whole cell process below 200 degrees Celsius, which means lower energy consumption during production. Next one is 120 micrometer thin wafer production. As you know, carbon emission of silicon material accounts for the highest proportion among all PV module components. Therefore, thin wafer will save silicon material greatly. The last one is high strength steel frame. Due to life cycle carbon emission calculation, it can reduce 77% compared to aluminum frame module. So in this case, we can get very low carbon footprint value. Okay, this slide just shows that our Hyper-ion series products are compatible with all mainstream inverters worldwide. And for LCOE calculation, we simulate the 100 megawatt fixed tilt installation in Hainan, China. The result shows that Hyper-ion outperforms 10% compared to PERC and the TOPCon technology. Another thing we need to talk is about transportation cost, because right now this cost is very high. And from our calculation, Hyper-ion with 700 watt can save 23% transportation cost compared to 610 watt TOPCon module. So in this case, if we combine the full supply chain costs, including like wafer slicing, cell module, and the transportation cost, from our calculation, we can achieve the total cost very similar to PERC product. So I will summarize the Hyper-ion product advantages here. First one is we are using very thin wafer, which is 120 micrometer, and we have a patent 24 busbar module technology. In this case, we can use very thin wafer without breakage issue during lamination. And the second one is we can provide better cost and performance value. According to our simulation, levelized cost of energy of Hyper-ion product is 10% lower than PERC product. Next one is we have higher reliability, which can pass 5 times IEC spec. Then lowest carbon footprint. According to third-party simulation, it will be lower than 400 carbon value. So final one is we want to update our capacity planning. We are building the first 5 gigawatt cell and the 5 gigawatt module factory right now. And the tool will move in our factory next month. And the target to produce first cell at the Q1, roughly February, the end of February next year. And the second half of next year, we plan to build another 10 gigawatt. That means finally we will have 15 gigawatt cell and the 15 gigawatt module heterojunction factory at the end of next year. Okay, thanks for attention.
Okay, thank you, Po-Chuan. That was really very nice presentation. And yeah, it's also very nice to see that you're also ramping up and going to gigawatt scale manufacturer. So I have a few questions. One question is really regarding the wafer size. Ryzen was one of the early adapter, I think the first company to adopt the 210 wafer format, and then followed by Trina Solar. But Trina, they have also came out with this G12R size. So are you also evaluating this wafer size?
Yes, of course. We can got the N-type G12 wafer very easily in China. We have several vendors.
No, my question is G12R, which is 210 by 182.
Sorry?
G12 by, so 210 by 182. So the width is 182 and the length is 210. So the G12R, like Trina is doing.
You mean compare G12 and the M10 wafer size?
Okay, no, because Trina Solar kind of came out with this new size of the wafer, which is 182 by 210. So it's not a square, but it's a rectangular one. So because, somehow it looked like you and Trina, they were very strong promoters of 210, and now Trina came out with this new size. So I just want to know, I was also curious if you are also going to do that.
Oh, no, of course not. I think there are different stories for PERC and the heterojunction industry. For heterojunction right now, we will do G12 half wafer. That means we cut a wafer at the beginning of a cell process. That is because actually, in this case, we can save the INGA process cost, but we can use thin wafer through half cut wafer, because heterojunction can use a very thin wafer. But of course, for other technology, they are looking for some different wafer size, or sometimes that is because they will upgrade their old factory. So in this case, they will find the best wafer size to upgrade, like in PERC factory or their TOPCon factory. So in this case, they can increase their depreciation time, Yes, but for the heterojunction, it's total different condition. We are a whole new factory, so we just focus on which size we can get a very thin wafer, and we can save the INGA cost.
All right. And you mentioned 120 micron. So is it production ready? So you said in your 500 megawatt factory, you started it. So is it really in the mainstream production, or you are still evaluating the 120 micron?
No. It is in production in our pilot line, 24 hours right now. Yeah. And so our pilot line is 500 megawatt capacity, and everything I introduced in my presentation file is what we are doing in our pilot line. So we already run all of this design over 6 months. So we have very high confidence we can just introduce all of this material in our 5 gigawatt cell production.
Oh, okay. So this was actually my next question, if you are going to introduce it in your 5 gigawatt production line. So one quick question, you said 10 milligrams per wafer, the low silver route. So is it 10 milligram per wafer is what right now, or are you going to reduce this much?
No, we are doing it right now. Just like I mentioned, yeah, we do it every day, 10 milligram per watt every day.
And what is the reference? So what's the typical regular low temperature cured paste? What it would be? How many milligrams per watt?
Normally, other company, they are doing like 20 or 25 milligram per watt, pure silver.
Pure silver. Okay, great. Actually, I have really a lot of questions, and also there are a lot in the chat room. So please stay back and answer these questions.
Okay, thank you.
Okay, thank you for the presentation.